All right, so this video is going to focus on characteristics of solutions. Solutions are homogeneous mixtures that are able to form when compounds that consist of ions or polar molecules, or even sometimes nonpolar molecules, are mixed with one another. They can be found in a range of states. You can have an all solid mixture, you can have an all liquid or an all gas mixture, or you could have combinations where your solute is solid and it's dissolved in a liquid solvent. Vice versa, all sorts of combinations can exist. The macroscopic properties do not vary, so the ones that we would visibly see don't vary, as opposed to the ones in heterogeneous mixtures that do. So like when you can physically see a solid separate from the solution, it's the liquid it's surrounded by, that would be a heterogeneous mixture. When you no longer can see this solid because it has dissolved in the solvent, that would be an example of a homogeneous mixture. You can have mixtures form that either have the same type of intermolecular forces, or you can have them form between those that have different intermolecular forces. If different types of intermolecular forces are present, typically you're going to have other types of interactions involved, such as dipole-induced dipole or ion dipole forces. We can separate the components of a solution by taking into account the different types of intermolecular attractions that exist between the components or even among the components. And so some examples include chromatography and distillation. When a solution is formed, it can be endothermic or exothermic. It's really dependent on what types of intermolecular attractions or interactions there are, both before and after the dissolving process has taken place. So with your solute and with your solvent, they need to expand. They need to make space so that that solution can form. Usually the expansion is an endothermic process, and when they are mixed together in step 3, that is an exothermic process. When the overall process is exothermic, that step 3 released more energy than steps 1 or 2 required. There are times when you can have spontaneous dissolving processes where step 3 is not as exothermic as step 1 and step 2 are, but those are pretty limited. You typically are going to have salts or any sort of dissolving process take place that it's more likely for heat to be released than for energy to be absorbed overall when it's all said and done. So I told you that there can be interactions that can occur between molecules or ions that do not share the same types of intermolecular forces, and that when these occur, you can still have these these substances with different types of forces dissolve in one another, but we have different interactions that take place to allow that to happen. So dipole-induced dipole interactions are one of these. This is how we are able to dissolve nonpolar substances in things like water. Or it would be how you might be able to get some salt to dissolve in hexane. So what will happen is that the polar molecules will get close enough to the nonpolar molecules that they distort those electron clouds and create those instantaneous dipoles. So that if the negative end of a polar molecule gets close enough to nonpolar molecules, it will cause the electrons to shift to the opposite end, so that molecule will then have a partial positive charge. So again, you can't have two negatives attracted to one another. They would repel. You need to have a negative attracted to a positive. You will have more of these, or you will have a strength increased when it comes to these types of interactions, depending on the molecule's polarity and on the number of electrons that are present in your nonpolar substance, how easily it can be polarized. And that could have to do with electrons, the size of your electron cloud, or if there is multiple bonds, pi bonding involved. And so this happens when bromine dissolves in water as well as when iodine dissolves in water. Ion dipole forces are what allows ionic compounds like salts to dissolve in water. They don't have the same type of intermolecular force. But when those ions get close enough to those polar molecules, they will form these ion dipole forces. They are definitely stronger than your dipole-induced dipole, or even just the dipole-dipole interactions that we see between polar molecules. And quite often they are even stronger than what we would see in a covalent bond, which is why salts that are capable of dissolving in water will do this quite readily and stay in that form because of the forces that develop between the ions and the polar molecules. So some factors that can affect your solubility, one is pressure. This is going to be specific for gases. Gases solubility will increase with pressure increasing. So solids and liquids being incompressible are not going to have an impact. This is why when substances are being prepared that have gases stored in a solution form, that gas is put in there, like with soda, at high pressures. That's why you hear kind of the fizz when you open up something that has gas dissolved in it, because now that pressure is being reduced and that gas then can escape. It's no longer as soluble. Temperature will also play a role. Solids are going to dissolve more rapidly at higher temperatures, but the amounts will vary. But gas solubility definitely decreases with increasing temperature. If you have a soda in your car in the summertime and you open it, if it's nice and warm, you will have a lot of gas come out quite quickly because it's at a higher temperature and it's been stored under that high pressure. If it is more at the temperatures we have right now, you would not see it escape as readily because it definitely would not be as warm. There would not be as much of a temperature change. So the curves on the left are representing the solubilities of these different salts. At any point on the curves for those different substances, that is the maximum amount of that solid that can dissolve and be completely dissolved into 100 grams of water at those temperatures. If you had less than that amount, that's typically what we will have when I prepare solutions for you all. We have an unsaturated solution. And when we have greater than that amount, we have what we call a supersaturated solution. And that's how crystals can form. You'll notice for the gases that they mostly decrease as we're going across. And that for some of those solids, you will see their amounts start to diminish as the ionic solids as the temperature increases. I would imagine some of the factors at play are that those are some pretty large molecules, especially with like cerium, and that is probably having a little bit of an impact on its ability to dissolve in water. So which of these solvents, water or hexane, would dissolve the following substances? Remember that water is very polar. It's got hydrogen bonding taking place, while hexane is very nonpolar. It's got a lot of London dispersion forces. So if we look at NaCl, NaCl is an ionic compound. It is a polar molecule. And so because of those electrostatic forces that are present, it's more likely to dissolve in water. It will stay dissolved in water due to the ion dipole forces that will form between the ions of sodium and chloride with water molecules that are very polar. HF forms hydrogen bonds. It's a polar molecular compound, and so it's going to dissolve in water as well. It has the same type of intermolecular force. They both have hydrogen bonds. Octane is similar to hexane in that it's just made of a bunch of carbons and hydrogens bonded to one another. Carbon and hydrogen are similar in electronegativity. They are nonpolar molecules, and because of that, they just have those London dispersion forces present. So it would be hexane because of the type of intermolecular force being the same in those two substances. NH3 is able to hydrogen bond as well. It's a polar molecular compound. So NH3 would also dissolve in water since both of them have hydrogen bonds. And then finally in letter E, we have that methyl group and we have the carbon double bonded to the O, and then we have an OH. And remember, when O is bonded to H, you have hydrogen bonding occurring. So this one Could dissolve in both, but it's more likely to dissolve in water because of that polar component with the hydroxyl group present. I will tell you, however, if that carbon chain had been much longer, if instead of having CH3, we had had like C8H17, we had had an octane-like chain attached to that carbon, because there was an overwhelming nonpolar component to that molecule, it would have been more likely to dissolve in hexane than it would have been in water. So you do need to keep in mind that it's not just the type of force, but the amount of forces present that will have an impact on the dissolving process. Here I want to know which of these would be more soluble in water and why. Again, water hydrogen bonds is a polar molecular compound. We have two polar molecules here, NH3 and pH3. If you draw out their Lewis structures, you will see they each have one lone electron pair. But NH3 can hydrogen bond, pH3 cannot. So although they both are soluble in water, NH3 would be more soluble because it has the ability to have the hydrogen bonding. pH3 could have some dipole-dipole interactions with water, as can NH3, but only the hydrogen bonding can be done with NH3 and water. In part B, we have CH3C triple bonded to N, and then we have ethane CH3CH3. Ethane is going to be very nonpolar. It's only going to have London dispersion forces because it just has the carbons bonded to each other and to the hydrogens. While in the first compound, CH3C triple bonded N, sorry, I don't remember the name for that one. I want to say it's methyl nitrile, but don't hold me to it. That has definitely some polar components to it because you have the electronegative nitrogen atom triple bonded to the carbon, and that carbon is then single bonded to carbon with 3 hydrogens. There's definitely asymmetry in this molecule. And so CH3C triple bonded N, having that polar component, is going to be more soluble in water because it's going to be able to have those dipole-dipole interactions. It will not be able to have those as readily with CH3CH3. That one would have the dipole-induced dipole if it was going to have one. And dipole-dipole is definitely stronger than dipole-induced dipole. Finally, in letter C, if we take a look there, we see that the only difference between the two molecules is the OH after the C double bonded O in the first molecule, and the CH3 which is bonded instead to the O in the second molecule. So they both have a polarity to them. They both have some asymmetry to them. But the first molecule that I have listed there, I want to say that's methanoic acid. It has a hydroxyl group, which means it can hydrogen bond. The second molecule can have dipole-dipole forces because it is polar, but those dipole-dipole interactions are not as strong as the hydrogen bonding, which is present in water. So it would be that first molecule, and again, the same reason as NH3, because they can both dipole-dipole or form those dipole-dipole interactions, but only the hydrogen bonding is present for NH3. For CH3, C double bonded O, OH. Again, if the carbon chain had been significantly longer, if it had been significantly longer for either molecule, the hydrogen bonding would still, the one with the hydrogen bond still would have been more soluble, but you would have probably reached a point where there wouldn't have been a whole lot of difference in their solubilities if that carbon chain had extended. So why can nonpolar molecules like CO2 dissolve in water? And why can ionic compounds like calcium chloride dissolve in water? So carbon dioxide is able to dissolve in water even though it is very nonpolar because it has those London dispersion forces. It has the ability to form those instantaneous dipoles with its electrons as they are moving about the atom, moving around the nucleus in their orbitals. Water has the permanent dipole, it can hydrogen bond, and because it has that permanent dipole, it can cause temporary dipoles to form in those carbon and oxygen atoms making up CO2. And so when those temporary dipoles are induced, that will facilitate the dissolving process of CO2. So the dipole-induced dipole interactions that can occur due to the polarity of water and its ability to asymmetrically distribute the electrons in the carbon and oxygen atoms, creating those instantaneous dipoles, allow it to be able to dissolve. Calcium chloride is an ionic compound, very polar. It has those electrostatic intermolecular forces. Water still just has the hydrogen bonding as its dominant intermolecular force. So they don't share the same type of intermolecular force, but remember we talked about how they have the ability when they come in contact with one another to form ion dipole forces. And those ion dipole forces that are generated can be stronger even at times than covalent bonds. And the water molecules basically surround the negative oxygen component of water, surrounds the positive calcium ions, and the positive hydrogen atoms in water make a sphere around the negative chlorine ions, and that facilitates the dissolving process. So here's one of those solubility curves, just asking you some questions to make sure you're comfortable with how this solubility curve works. Which of these has the smallest solubility at 10 degrees Celsius? So I would look at 10 degrees Celsius on my x-axis. I would want to find the one that has the smallest solubility, the smallest value for y, and that would be CaCl3. And its solubility would be around 5 grams. It's between 0 and 10 per 100 grams of water. Which two have the same solubility in water at 37 degrees? So I would go find 37 degrees Celsius, and I want to move up to where I see two curves overlap. And it looks like that happens at NH3 and KCl. NaCl looks just slightly above those. And then finally, which one has the greatest solubility increase as we move from 10 to 50 degrees? So which one has the steepest slope? And that one would be KNO3. And then these are just some questions to make sure you're comfortable with understanding how to use this graph to determine if a solution is saturated, it could not dissolve any more solid, unsaturated, or supersaturated. If you are unsaturated, you will have an amount below the solubility, the point on the graph. If you are saturated, you will be directly on the graph. You will be at that solid solubility. If you're above it, you have more solid that's in solution than is capable of dissolving. That's when you would have a supersaturated solution. So if I look at 60 degrees for KCl, so I'm going to go find KCl at 60 degrees, and I have 40 grams in solution. So I'm going to come back down to 40. I see that that point is below the KCl's solubility curve at that temperature. So as a result, this would be an unsaturated solution. If I look at NaNO3 and I'm at 40 degrees, and I have 105 grams in solution, so I'm going to go up for 40, go find 105. I see that that happens to touch virtually on the curve for NaNO3, so that would be a saturated solution. Finally, for NH4Cl, I'm at 80 degrees, and I have 80 grams. So if I have 80 grams in solution at 80 degrees, so let me go find my NH4Cl curve, which happens to be just below it. Because that point is above the curve, I would have a supersaturated solution.